Now we get to electron configurations. So we talked about quantum mechanics and a bit about the behavior of electrons in atoms, and we talked about how the electrons exist in orbitals, and orbitals are different than orbits. We understand what an orbit is. It's like the Earth going around the sun, and that's Bohr's model of the atom, which is easier to think about, but unfortunately incorrect. Orbitals are regions of space, volumes where an electron is likely to be found. Remember that electrons have wave properties and particle properties, and so I find it easiest to think of these orbitals as a standing wave of the electron. When we make a description for a given atom of the orbitals that are being occupied by electrons, we call it an electron configuration. I've got a slide here coming up where I really spell out my hotel example, but I already told you about it, so I can use it. The electron configuration is a little bit like the guy at the front desk making notes. Okay, who's staying, how many people in this room, how many people in that room, so that the next guy coming in, he can say, okay, you're going to be in this room. It's just a shorthand of where the electrons are. So for hydrogen only has one electron. It's a nice place to start. The orbitals are differ in energy, and the electrons are go into the lowest energy orbitals first. So for hydrogen, its one electron is going to be in the 1s orbital, and so we indicate that as 1s1. Electron configurations are a place where chemists do write the number 1. So 1s1 means that there's one electron in this 1s orbital. We can do calculations with Schrodinger's equation that show that hydrogen's one electron is in that lowest energy orbital in the atom. Unfortunately, for all the other atoms that have more than one electron, the equation cannot be exactly solved. There are extra terms that have to be considered because electrons interact with each other, and so that's a complication that doesn't occur in hydrogen. But all of the approximate solutions show that the orbitals in other atoms are like those in hydrogen, and that's good enough for us in Chem 1A. The two things that we do need to think about in multi-electron atoms are electron spin and energy splitting of sublevels. So electron spin, this is the fourth quantum number m sub s, and it has values of +1/2 or -1/2. So we can think of this as spin up or spin down. It's just a property of the electron. So I just talked about electron configurations. An orbital diagram is a more visual way of representing the same information. So for hydrogen, the orbital diagram, we're going to have a box. The box represents the orbital. And so this is the 1s orbital, and in that orbital, there is one electron. And so we represent that as an arrow pointing up. It's a half arrow. It only has 1/2 of its head here, and that's pointing up. And this works really well with my bed analogy in the hotel, right? So, here's the bed with this, I'm going to get fancy now, it's got pillows, right? And so that arrow pointing up, I imagine to be this first person sleeping right side up in the bed. If another electron comes into that orbital, it has to have the opposite spin. And so the other person sleeping in the bed is going to sleep upside down because they really don't want to be sleeping together, but the floor is lava, and so they have no choice. They have to sleep in the bed. So this is what they do. I made up the analogy. I can say whatever I want. In a group of hydrogen atoms, each atom only has one electron. About half of the electrons are spin up and about half are spin down. And for most purposes, whether it's spin up or spin down doesn't matter. I'm just going to erase this because I don't want this to misrepresent hydrogen. So if we draw an orbital diagram for an atom, we don't know if that particular atom is spin up or spin down. Doesn't really matter. So we just always write the first one spin up, just by convention. So the Pauli exclusion principle says that no two electrons in an atom may have the same 4 quantum numbers. This is like saying no two citizens may have the same social security number. We have to have a unique identifier, just like no two students. Maybe it'd be better to say your student ID number. You can't have the same student ID as someone else, right? Because it would cause all kinds of problems. Each electron has its own unique set of 4 quantum numbers. So if you look at atoms in the same orbital, so let's think about that hydrogen. Well, actually, let's think about helium, which we haven't quite gotten to yet. But helium has 2 electrons, right? And they're both going to be in that same orbital. This is a 1s orbital. And so if we look at the quantum numbers, there's N, there's L, M sub L, and M sub S. For the 1s orbital, what's the value of N? 1. That's indicated by the 1. What's the value of L? It's 0. So L can be from 0 up until 1 less than N, and it goes 0, 1, 2, 3, S, P, D, F. We use letters instead of the numbers. So both of these electrons being in this 1s orbital have the same N and L quantum numbers. And then in this orbital, what's M sub L? It would have to be 0. Because M sub L goes from negative L up to positive L. So from negative 0 to positive 0. So it's 0, right? So far, those 2 electrons are going to have the same quantum numbers because they're in the same orbital. But one of these is spin up and one is spin down. This one's plus 1/2, and this is minus 1/2. So the set of quantum numbers is very similar, but the last digit's different, okay? There's probably someone else at Fresno City College who has a student ID number that is the same as yours except for the last number, right? But it's different, and that indicates them, and yours indicates you. So every electron has to have its own identification number, set of 4 quantum numbers. So in an orbital, we can only have 2 electrons, and they have to have opposite spin. Otherwise, we'd have 2 electrons with the same set of numbers. So the Pauli exclusion principle says we can only have 2 electrons in an orbital, and they're going to have opposite spins in order for them to have different quantum numbers. That make sense? If we know how many orbitals are in a sublevel, it allows us to determine the maximum number of electrons in the sublevel. That's nice, but I don't think it's really worth talking about. Let's look at helium, which we just did. Yeah, I get ahead of myself sometimes. So there's the orbital diagram. Helium has 2 electrons. Here are the quantum numbers. We just went through doing those. We see that there's a little bit of difference here. The electron configuration for helium would be 1s2, because I'm indicating that there are 2 electrons in the 1s sublevel. So in the hotel, the 1s room has 1 bed in it, and that 1 bed can hold 2 people. And so this is telling the hotel clerk at the front desk, room 1s is full, it's got 2 people in it. And the orbital diagram actually shows the bed with the people sleeping in it. Maybe a little creepy. Yeah. What about that sublevel splitting? In a hydrogen atom, all of the sublevels in a principal energy level have the same energy. On the hotel model or analogy, all the rooms on the same floor have the same price. Doesn't matter which room you're staying in. If you're on the 3rd floor, all the rooms are the same. Orbitals that have the same energy are called degenerate. When we have more electrons, then the energies of the sublevels get split. So then the rooms on the 3rd floor, the S room is less expensive than the P room, and the D room is more expensive. And this is caused by charge interactions, shielding, and penetration. So in general, within a principal level, the lower the value of L, the lower the energy of the orbital. So S is a value of 0, P is a value of 1, D is 2, F is 3. In the hotel, I think of the S room as being closest to the elevator, because when we draw the diagrams, they all end up on this side. It seems logical that the elevator would be over there. And then as you go down the hallway, you're getting further and further from the elevator, so I can imagine, well, the rooms that are further from the elevator cost a little more because they're quieter. You don't have people traipsing back and forth. Maybe the ice machine, people getting ice at 3 a.m. makes a lot of noise, and so that 1S room or the 2S room is a little cheaper because it's kind of noisy. I don't know. I have to make up reasons for things so I can remember them. Coulombs Law is useful in helping us understand a number of things involving electrical charges. This is the full equation here. We don't really need most of this. What we need to remember is that the energy, the potential energy of 2 charged particles, is proportional to the product of their charges divided by the distance between them. So this part here is just a constant, and so we don't really need to remember what that is. When we have 2 charges that are the same, 2 negative charges, they repel each other. And then the potential energy is positive, meaning it's not stable. Those are repelling each other. If the charges are opposite, we have a positive and a negative, then E is negative, and as the potential energy increases as the particles get closer together. So as R gets smaller, the energy gets larger. If it's negative, it's getting more negative, which is more stable. So it depends on the distance. It also depends on the magnitude of these charges. If they are +1 and -1, or +2 and -2, there's going to be a difference in the amount of attractiveness. So we could have 2 weak magnets and they'll kind of stick together, or you can have 2 really strong magnets. Have you ever taken apart a hard drive from a computer? There's some really cool magnets in there, and they stick together really well. So electrons have negative charges. They are going to influence each other in the atom. So we've got attraction between the nucleus and the electrons, and then we have repulsion between pairs of electrons. 2 negative electrons don't want to get too close together. So these cause, the repulsions cause a net reduced attraction to the nucleus. We say the electrons are shielded from the nucleus. The total amount of attraction that an electron feels for the nucleus is called the effective nuclear charge, or ZF. Z is the atomic number, the number of protons in the nucleus. Penetration has to do with how close the electron gets to the nucleus. The closer it is, the more attraction it experiences. So when we have electrons in higher energy orbitals, in the Bohr model, we just think, we just have these circular orbits and they're getting further and further away, and so you see that a higher energy electron is just playing farther from the nucleus. But understanding the shapes of the quantum mechanical orbitals, they do overlap with each other, and so some of those orbitals allow the electron to get closer to the nucleus than others do, and that's called penetration. So the electron can penetrate the electron cloud of the inner electrons, and that will allow it to have more attraction for the nucleus. So let's explain this with pictures. So this is a lithium atom. You can tell that because it's got a positive 3 charge in the nucleus. So the lithium atom, in that first energy level, there are 2 electrons. Those are in the 1s orbital. And then this third electron is in the 2s orbital. It's up on the 2nd floor of the hotel. And so this electron, on average, is farther away from the nucleus than these 2 electrons. And so these electrons kind of get in the way of the attraction that this electron has with the nucleus. We could think of it as, well, this is in an outer level, and so it's seeing this as a whole, and so it's seeing 3 positive charges and 2 negative charges. That's a net attraction of about 1 plus. Okay, another kind of weird analogy for this is, regardless of what sex of person you're attracted to, think of that really hot person on the beach, right? So these electrons are seeing that person in a skimpy bathing suit. And this electron out here is seeing that person wearing street clothes, right? T-shirt and jeans. And so you're not seeing all of the attractiveness of that person. Does that make sense? So these guys on the inside are more attractive because they get to see more of the person. And then the farther out you go, the more clothing the person has on. And these guys out in like the 4th level, this person's wearing a parka and a ski mask, and you can't even see what shape they are or anything. And so it's hard to be very attracted to someone dressed up in a parka, right? Does that make any sense? I got a little smile from one person. I'll take it. This electron in that 2nd level, if it can get into the region of that 1st level, that's called penetration. If it can penetrate into the space occupied by those other 2 electrons, then it's seeing the full force of the attractiveness of this nucleus. I guess taking the clothes off, I don't know. It breaks down a little bit. But that's penetration. This gets in here, and now it's not getting blocked by these other 2 electrons. So it's got a full 3 plus charge. Yes?
Would that electron ever go back to its original orbital?
Yeah, so an important thing is when penetration occurs, it's not because the electron has left its orbital. So I haven't explained how that happens yet, but that's coming up real soon. The orbitals do cross into each other. They overlap. So here we have that radial probability versus distance from the nucleus. And here's the 1s orbital, and it's so high here that we just cut it off because we didn't really need to know how high up here it went. But so this is telling us that as we move out from the nucleus, the probability of finding an electron in the 1s orbital is very high in this region, of a little above 0 up until, 150 or so picometers, and then it really starts to fall off. Okay. The 2s orbital is also a spherical orbital. It's larger in size, and so the most common distance Most probable distance is out here at almost about 300 picometers. But this orbital has a node, and so there's a little blip of probability here, and then a node, and then the big part of the probability. And so an electron in the 2s orbital can be over here very close to the nucleus and in the space of the 1s orbital. So this is the penetration of 2s. The 2p orbital does not have an extra node, and it does penetrate a little bit. It overlaps here, but not as closely, and then most of its probability is out here at a greater distance. Okay? Anybody have any questions about that? Yeah.
Can we start one more time? Sorry,
Yeah.
So R is in reference to the distance from the nucleus, or
R is the distance from the nucleus, and so this line shows us the probability of finding the electron at that distance. So in an electron in the 1s orbital, if you're looking at 600 picometers, the probability of finding the electron is basically zero, just minuscule. The probability of finding it, I think it was 52.9 picometers, was the highest probability.
And this is for hydrogen?
That's for hydrogen. That's for hydrogen. And so in the 2s orbital, the most probable distance would be out here. But again, the electron is not a particle orbiting like a planet orbiting the sun. It's easier to think of it that way, but it isn't. It's a standing wave, a three-dimensional standing wave around the nucleus. And in that standing wave, there's a little bit of it here, and most of it's out here. But the electron occupies that entire volume, because a wave is not limited to being one place, right? So it occupies the entire shape of that orbital. The 2p orbital also overlaps with the 1s orbital, but not as much and not as close. And so what's important is how close could that electron get to the nucleus? So the 2s electron, its orbital is closer on its edge there to the nucleus than the 2p orbital is. So because the 2s electron can get closer to the nucleus, the energy of it is lower than the energy of the 2p orbital. Is that starting to, yeah. So it's wonderful if you understand what I'm talking about here. You can pass the class, you can do well in the class without understanding that. But it is my duty to try to explain it to you. It helps to understand. But some of you can say, well, she sounded like she knew what she was talking about, so I'm just going to go with that, right? So because of the penetration of these different orbitals, the sublevels in each principal level are not degenerate. Okay, so that's got all these big words, and I personally find sublevel, orbital, and principal level to be a bit confusing, right? And so I transform this into the hotel in my brain when I talk about these things. So because of penetration, the rooms on each floor are not the same price. Okay? So I don't really have an analogy for penetration when it comes to the hotel, but the 1S room is the cheapest. It's the closest to the nucleus. The 2S room is a little closer because of this penetration to the nucleus than the 2p room. And so it's going to be cheaper. The closer to the nucleus, the more attraction, the lower the energy. Lower energy is good. Things want to go to low energy. The lower the cost for staying in that room. When we get higher into the 4th and 5th floors, principal levels, the effects of penetration become even more important, and now the 4s orbital is lower in energy than the 3d orbital. So even though the 3d room is on the 3rd floor and the 4s room is on the 4th floor, the 4s room is actually cheaper. Does the pricing of hotel rooms always make sense? No, it doesn't, right? It seems kind of random sometimes. And so we just kind of, if we're not understanding the idea of penetration, we're going to say, well, it's one of those weird hotel things that we don't understand. And we just recognize that this is how it is. The other thing that happens as we get farther from the nucleus is that the difference in energy between the levels becomes smaller and smaller. And so then penetration, a small amount of penetration can have a larger effect on the overall energy. And then just to make things more fun, the relative energy ordering can actually vary among elements. We're going to ignore that in Chem 1A because we can. We're going to pretend it's the same for everything, but it does change. So here's the general energy ordering of orbitals for multi-electron atoms. And this is, I think of this red thing here as being the elevator in the hotel. And so here we have the 1st floor, and here we have the 2nd floor. And this is not representing necessarily how high they are, but the price. So the farther up you are, the more the room costs. So this is the cheapest, and then this room is next, and then this room, then this one, and so far everything's making sense. But then this 4s room is cheaper than the 3d room. And it's because of penetration, or we can just say, well, that's the way it is. And I'm going to show you in a minute how we can see this ordering on the periodic table. It's on there, it's hiding in plain sight. So 4s and then 3d, and then the next highest is 4p, and then 5s and 4d, and it's just, it's all crazy mixed up after that. But this is the energy ordering, and so it tells us how the electrons fill, the orbitals fill. And so when we're looking at where are the electrons for, say, zinc, 30 electrons, we're just going to start with the lowest energy orbital, and we're going to fill them up. And we're just going to keep filling in the order of energy until we get 30 electrons in there. One more thing to consider is the Aufbau Principle. And this is that electrons occupy orbitals so as to minimize the energy of the atom. So the lower energy orbitals fill before the higher energy orbitals. Electrons are cheap. They want to stay in the cheapest room possible. Trying to save their money to play the slot machines, I guess. Orbitals in the same sublevel have the same energy. So that makes sense at least. In the hotel, that means that, in that P room where there's 3 beds, they're not going to charge you a different rate depending on which of those 3 beds you sleep in, right? They're all going to be the same. They're going to charge you the same amount for whichever bed you choose. Because how would they enforce that, That's invasion of privacy, most likely. This is the filling order. And again, I'm going to explain how we can find that off the periodic table. Orbitals can hold no more than 2 electrons each. So you can't have more than 2 people sleeping in a bed. And the spins have to be opposite. And then Hund's rule says that when we're filling degenerate orbitals, electrons fill them singly first with parallel spins. And this works out in the hotel analogy as well, because let's just say we have a P room with 3 beds. So it's got 3 orbitals. And I'm just going to show them next to each other because that works out better. It's more like the orbital diagram. So let's imagine electrons coming into this room. The first electron is probably going to take the first bed closest to the door. They're really, really tired. They had a big day, right? Comes in, lays down in the bed. The second electron comes in. Remember, this is like guys staying in the same hotel room. Second guy comes in. Does he want to sleep in the same bed as the first guy? No. No, he doesn't. He's going to sleep over here. He's going to take his own bed, right? I mean, anybody would do that. Women would do that too. This happens on a bus. Public bus, school bus. You come in and none of these people are your really good friends. Are you going to sit next to somebody you don't know, or are you going to take an open seat? You're going to take an open seat, right? That's just bus etiquette, right? You don't sit next to someone unless there's no choice. You have to sit by someone. Then you pick the most attractive person or the least unattractive person, right? The person who doesn't look like they might smell bad. So the third electron comes in. What's he going to do? He's going to take his own bed too. And are they going to choose to sleep upside down in their beds? No, because normal people wouldn't do that. I've got my own bed. I'm going to sleep right side up because that's what we always do. Now, the fourth electron comes in, and he can't have his own bed. He's going to have to share with somebody. And because they think it's creepy, they're not going to sleep snuggled up next to each other because they don't know each other. This guy's going to sleep upside down in the bed just to avoid appearances of anything, right? Does that make sense? Okay, so that is the Aufbau Principle and Hund's rule. You're going to put them in separate orbitals in that same room, same sublevel, because the energy is the same. And we're going to just put them spin up. And then when the next one comes in, once all of them are half full, next one comes in, they'll start to pair up with opposite spins. Pardon me?
So the principle and the rule are the same thing, do you know?
Yeah, my slide doesn't really define what the Aufbau principle is. It has to do with the filling of the orbitals from the lowest energy.
So Hund's rule applies in the umbrella.
Hund's rule is filling degenerate orbitals first with parallel spins, and then pairing up. Yeah. And I'm not going to quiz you on the names of these principles and rules. I may refer to them though, because sometimes it's easier than saying the whole thing out. Yeah. Okay, so here's the slide that lays out the hotel analogy. So this is the Quantum Hotel. That's the name of the hotel. It's a discount resort for electrons in Mrs. K's chemistry land. It's like Disneyland, but it's chemistry. First floor has one room, it's the S room. Second floor has two rooms, S and P. Third floor has three rooms, S, P, and D. Each S room has one bed, P rooms have 3 beds, D rooms have 5 beds, F rooms have 7 beds. You can only have 2 people per bed, and they have to have opposite spins to sleep upside down. So the correlations, in the hotel, a floor corresponds to a principal shell or principal energy level. The room is the subshell or the sublevel. The beds are the orbitals, the people are the electrons, and money is energy. Okay? And I just find talking about the hotel makes it a lot easier to remember this stuff, because then it has some relevance to real life, right? So then we can look at this energy levels. I forgot what the name of that was. Anyway. And so then we can imagine putting electrons in here. And let's just pick something maybe kind of interesting. Let's do iron. Iron has 26 electrons. So we're just going to look at, well, what would happen if iron came here, 26 electrons? Maybe iron is a bus, a tour bus that comes in with 26 people, and we're going to dump them on the hotel, right? That's a new twist. to the analogy just invented right now. So watch as I put the electrons to bed. Okay, so I put 1 in here, 1, 2, because they're cheap. He doesn't want to pay a lot more to get his own bed. So there's 2, and then 3, 4, 5. He has to pay more. There's no choice. And number 6 is going to go over here. Because why not have your own bed if it costs the same amount of money? And then 7 comes over here. 8 says, well, because cheapness wins out, I'll just sleep upside down in this bed rather than paying extra money for my own. 2, 4, 6, 8. I'm up to 8. Then 9 and 10. And then electron number 11 has to go up here. And then 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and that last one is going to share that first bed there. So that's how we fill them in, and then the electron configuration is just a shorthand describing what's going on here. So start at the bottom. The 1s has how many electrons? 2. So this is 2. 1s, 2. The next room is the 2s room, and how many electrons in there? 2. And then we get the 2p room. How many electrons? 6. Next is 3s with 2 electrons, and 3p with 6 electrons, and then 4s with 2 electrons, and 3d with 6 electrons. That's the electron configuration for iron. Any questions right now? Yeah.
No, I'm later.
Okay. Yeah, I'm not done talking about it, so this is just like the first big one. So just some notes here. Unless otherwise stated, electron configuration refers to the ground state. Electrons can get excited. You zap an atom and it can absorb energy, and the electrons can go to a higher level, and then they'll come back down and they can emit light. And we talked about that in chapter 8. When we say write the electron configuration, unless it says it's an excited state, we assume it's the ground state. The number of electrons in a neutral atom is equal to its atomic number. So how did I know that iron has 26 electrons? Well, iron is number 26 on the periodic table. The atomic number, 26, tells me 26 protons, 26 electrons. The arrangement, I'm not sure that word parallel is correct in there. The parallel spins in the separate orbitals and then the paired spins within an orbital help to minimize the repulsion of the 2 electrons. Because you might think, well, you've got 2 negative charges. How can those 2 negative electrons occupy the same orbital? Well, that's why their spins have to be opposite, because that minimizes the repulsion. Just like the 2 guys sleeping in the bed, it minimizes the repulsion they feel if they sleep head to toe instead of next to each other. Each orbital can hold a maximum of 2 electrons, and so we can see here that we've got a possibility in the S of 2, P can hold 6, D is 10, and F can hold 14. And we can get that from thinking about the hotel as well. So the electron configuration is just a listing of the sublevels in order of filling, in energy order, showing the number of electrons in there as a superscript. So this would be the electron configuration for krypton. That's 36 electrons. So we were doing iron, and we stopped at 3d6. And so this has 10 more electrons, and so there's 4 more here, and then it goes up to the next level, and we get 6 there. As you can imagine, writing all of this out can get a little tedious, and the first part's always the same. So there is a shorthand, but you still need to know how to do it the long way. It's sometimes called an inner electron configuration or a noble gas configuration. That's the term I use. And in here, what we do is we use the symbol of the previous noble gas to represent the inner electrons for that one. Let's see here. So if we look at rubidium, rubidium has 37 electrons. So this is its full electron configuration. And one way you can check your electron configuration is if you add up all the superscripts, all those superscripts add up to 37. If they don't, then you screwed up somewhere. But if we look at this, we see that this part is the same as krypton. It's exactly the same, right? So instead of writing all of that, we write krypton in brackets, Kr for krypton. And this says the electron configuration of krypton and this other stuff. You can only do it for noble gases. Can't just pick the previous one. It has to be a noble gas. Yeah. Okay. So this one?
Yeah. So you started filling up 3D and you did them each. You put one in each.
Mm-hmm.
And then you went back to fill them up.
Right.
Why wouldn't you fill up each one of them fully first?
So like so if I'm going in, I got 1 electron and 2 electrons and 3 electrons and 4 electrons. And so what you're asking is this next one, why doesn't it pair up?
Yeah.
Because you want to sleep head to toe with a stranger when you can have your own bed?
Sorry.
Do you? No, because you're not weird, right? So obviously that's not the reason that they do that,
Right.
but we can remember that, right? The parallel, the orbitals with parallel spins is better than paired up electrons with empty orbitals. So the exact reason for that is beyond the scope of this class.
So only the S will fill up fully.
Yeah, with the s orbitals, here, so the first electron goes in here. The second electron doesn't go up to the 2p because he'd have to pay more money. That's higher energy. And so he's going to stay in this room. That means he's going to have to pair up. So they would prefer to have their own bed, but they're not willing to pay extra for it. Okay?
So the degenerates, right? That's what they're called. So the 3Ps, the 3 2Ps that are there, right? Those are degenerates. And we determine that by Sublevel.
So these 3 orbitals are degenerate. They are the same energy. And so, yes, you could say orbitals that have the same first 2 quantum numbers are going to be degenerate. In the hydrogen, if you have the same first quantum number, they're going to be degenerate. In a hydrogen atom, all of these 3 orbitals would have the same energy. But that's only true for hydrogen. So that's why we don't even bother drawing it that way. Does that help? Anybody else have questions? So here's some electron configurations we did hydrogen and helium, and now I'm just going to continue in the periodic table. So here's lithium. Lithium has 3 electrons. And so here's its orbital diagram. The orbital diagrams are typically drawn linear with, we're just, as we go to the right, they're higher in energy. Because if we drew that whole diagram every time, it'd be really a pain. So here we have the first floor, the S room, so 2 electrons are going to go in there, and then we have the second floor, the S room, and 1 electron is going to go in there. The other orbitals exist, but we don't draw them if they're all empty. We only draw the room that has rooms that have electrons in them. So then the electron configuration is 1s2, 2s1. 1s has 2 electrons, and the 2s has 1 electron. Beryllium has 4 electrons, and so that 4th electron is going to pair up in here, and we get 1s2, 2s2. Boron has 5 electrons. So these first 2 are full now, and so this 5th electron has to go into the 2p room. We're going to draw the whole room. The room has 3 beds. He's going to sleep in 1 bed, and the other 2 beds are going to be empty, but we're still going to draw them. So we're not just going to draw 1 bed from a room, we're going to draw the whole room. And then carbon, 6 electrons. That next electron coming into this room says, well, I'd rather sleep by myself, thank you. I'll take that next bed. Doesn't cost any more, so why not, right? Any questions? When we're first doing this, I think it's helpful to look at the orbital diagrams first, and then the electron configurations, because this is more visual. So here, this would be 1s2, 2s2, 2p, 2. The electron configuration doesn't specify whether these guys are paired up in the same bed or not. This is representing a sublevel, the 2p sublevel. In the 2p sublevel, there are 3 orbitals, 1, 2, 3. Each box is an orbital. That's easy to get mixed up. Okay, so let's write orbital diagram for argon and determine the number of unpaired electrons that it has. So I haven't shown you how to get the order off the periodic table yet, so I'm going to kind of do that part for you. So there's 1s and 2s and then 2p. And then we're up to the 3rd floor. We've got 3s and 3p. And everything's nice and orderly to that point. So I can tell that I've got enough rooms there. How many electrons does argon have? 18 electrons, because it's element number 18. So write the orbital diagram. We're going to fill these in, just counting to 18. 1, 2, 3, 4, 5. Now the next one, this is 3 beds in the same room, same energy. That's why the boxes are together. They're degenerate. So it's going to take his own orbital, his own bed. That's what, 6? And the next one, 7. Now they have to pair up because they don't want to go to higher energy. 8, 9, 10. Now they have to go up to higher energy. 11, 12, 13, 14, 15, 16, 17, 18. So if we wrote the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6. Yes?
So if you would do the noble gas configuration, would you just put argon, or would you have to go back?
That's an excellent question. How would you do the noble gas configuration for this one? Well, it'd be kind of cheating to just, it's like argon in brackets, right? This is not all that helpful. Probably not. You'd probably say, well, here this is what, neon? And so we could say neon in brackets, and then 3s2, 3p6. So how many unpaired electrons does argon have? 0. They are all paired up. And we'll find out later that that has some significance. 0 unpaired electrons. Any questions?